Hi everyone, welcome to my presentation on simple linear regression. I'm Mukunda Sharma, a PhD student at University of Northern Colorado. In this presentation, we'll delve into the methodology and application of regression analysis, specifically focusing on simple linear regression. Before we begin, let's differentiate between correlation and regression. Correlation measures the strength of the association between two variables, while regression predicts the value of a dependent variable based on an independent variable. Regression analysis allows us to predict and explain the impact of changes in an independent variable on a dependent variable. Let's explore the fundamentals of the simple linear regression model. This model involves one independent variable and describes the relationship between variables linearly, assuming changes in one variable affect the other. So we can see different types of relationship between the variables, like linear relationships, curvilinear relationships, strong relationships, and weak relationship. And also there may be no relationship between the variables. Let's examine the equation for simple linear regression. It provides an estimate of the population regression line incorporating the intercept, slope, and observed value of x. Here the model is fitted for the population. These notations are used for population. Y is dependent variable. Beta sub 0 is population y-intercept. And beta 1 is slope or coefficient of x. And epsilon is random or error term. Now we discover how we obtain regression coefficients using the method of least square. By minimizing the sum of square differences between observed and predicted values, we derive the regression equation. Here I didn't include the formula for calculating slopes and intercepts. You can find this formula from other sources. Let's understand how to interpret the intercept and slope. B sub 0 is the intercept here, and B sub 0 is the value of estimated average of y when the value of x is 0. It means when we put the value of x equals 0 in our regression equation, and the value of y would be b sub 0. And b sub 1 is the estimated change in the average value of y as a result of 1 unit change in x. If we change the value of x by 1 unit, then y would change by b1 times. Let's apply our knowledge to a real-world example. We will examine a dataset featuring how prices and sizes to illustrate space to illustrate simple linear regression in action. Here y represents the house price in $1,000 and x represents the independent variable square feet or area of the house. Visualizing the data helps us understand the relationship between the variables. If we draw a scatter plot of house prices against sizes reveals the pattern we will analyze. Using several statistical softwares like SPSS, Excel, R, we can generate regression results. Excel provides regression statistics, coefficients, ANOVA, and more, aiding our analysis. Minitab is another powerful tool for regression analysis. Its output includes regression equations, coefficients, ANOVA tables, and diagnostic plots for thorough analysis. Simple linear regression can also be seen in graphical representation. If we plot the value of y against the value of square feet, we can see this type of scatter plot. Let's interpret the value of intercept and coefficients or slope. Here the value of intercept is 98.24833. It means when we put the value of square foot 0, the house price would be 98.24833 in an average. But here the house cannot have a square footage of 0, so B sub 0 has no practical application in this example. And the value of B1 estimates the change in the average value of y as a result of a 1 unit increase in x. Here B1 equals 0.10977 tells us that the mean value of a house increases by 0.10977 thousand times. It means $109 on an average for each additional 1 square foot of size. And we can predict the value of house price if we know the value of square foot. Here, if we put the value of square foot to 1,000 square feet, we can find new price of house. The predicted price for a house with 2,000 square feet is $317.85 thousand or $317,000. It's crucial to recognize the limitation of our predictive models too. If we predict the value of y by using the value of x, which is out of range, then we may have a problem of extrapolating, and it is not considered as good prediction. So we have to predict the value of y if the value of x is given within a range. Let's practice with a simple example here. y equals 3 plus 4x is a simple linear regression. This is for you to practice to interpret the value of coefficients and intercept and predict the value of y as the given value of x. Here in this slide, we included the variation. Understanding variation helps us evaluate regression model performance. We'll explore total variation, explained variation, and unexplained variation to assess model fit. The coefficients of determination R square quantifies the proportion of variation in the dependent variable explained by the independent variable. The higher R square value indicates the stronger relationship between variables with values ranging from 0 to 1. In this graphical representation, here R square is 1. It means there is a perfect relationship between x and y. And also it can be said that 100% or total variation in y is explained by variation in x. And in this example, in this graphical representation, you can see the different type of relationships, different degrees of associations. The closer the value of R squared to 0, the weaker the relationship. If you found the value of R squared is 0, it means there is no correlation between the independent and dependent variables. Here the Excel output for R square. The value of R square is 0.58082. It means approximately 58% of the total variation in y is explained by independent variable x. It means 58% of the variance in house prices is due to the change in the value of square foot. Here are some formula to calculate standard error of estimate. And standard error of estimate tells about how on an average the values are scattered from linear regression line. Here the average scatterness of the value from regression line is 41 unit. We can interpret standard errors, and as per the standard error we can say that whether the association is strong or weak. The first graph shows the small standard error. It means all the values are concentrated to the regression line. And in the second graph, the values are scattered far away from regression line. Understanding and validating regression assumptions is crucial for reliable results. Assumptions include linearity, independence, homoscedasticity, normality, and absence of multicollinearity. Here, our model is simple linear regression. it means there is only one independent variable. So we don't need to take the multicollinearity here, because the multicollinearity is used to take the relationship between independent variables. Here independent variable is only one, so we don't need to take multicollinearity here. And after examining the assumptions, if we found that assumptions are not satisfied, we have to do some transformation or apply some remedies to control this violation. Otherwise, our results are not reliable. We can use residual analysis for linearity, and whether there is independence in residual or not. The residuals should be independent in our ideal regression model. We can check normality, because all the values of variables should be distributed in normal distribution. So we can use normality by using stem and leaf display, or box plotter residuals, or histogram residuals, or normality plots. So there is one remedies to control autocorrelation. Autocorrelation arises if we deal with time series data. This autocorrelation means there shouldn't be correlation between the errors. And the Durbin-Watson test is used whether the autocorrelation is significant or not, or residuals are correlated or not. In this test, we use S0 and S1, and in null hypothesis we say that residuals are not correlated, and on the opposite side there we have a statement of positive autocorrelation. And there is some measures whether we reject or accept the S0. And if the value of test statistics of Durbin-Watson test lies between 0 to lower limit of Durbin-Watson test statistic, then we gonna reject S0. And if the value lies between upper limit up to 2, and we do not reject S0. And if we find the value between lower and upper limit of Durbin-Watson, and we cannot decide whether there is positive autocorrelation or not. So here are some graphical representation and a real example, whether to reject or not, S0. And there is standard error of individual slope. Here there is only one slope, there is only one coefficient of x, so we can find the standard error of coefficient here. And we can use hypothesis testing here to examine whether individual x's are significantly associated with y or not. Here there is only one x, so we just want to check for b1 or beta 1. We use t-test here, and what we say that in S0 there is no relationship between x and y, and in the H1 we say the linear relationship exists there. So we have the value of B1 here, 0.1098, and using this value we can find the t statistics, and the t statistics is 3.329. Here we can compare this value with critical value, or we can directly use p-value, whether to reject and accept. If the p-value is less than our specified value of alpha, then we can say there is significant relationship between x and y. Here the test statistic value is 3.329 and the critical value is 2.3060. It shows that our test statistic value is greater than the critical value. It means we have to reject S0, saying that there is sufficient evidence that square footage affects house price. And also we can use p-value method here. And another test, f-test, is used to examine whether there is significant relationship between all independent variable and dependent variable. We gonna use f-test for overall significance. t-test is used for the individual significance of slopes, but here f-test is used to examine the overall model, whether it is significant or not. Here are some formula for f-test. We can find these values from Excel output, and we can interpret as we do in t-test. We can use confidence interval to provide a range of values within which we are confident the true parameter lies. We'll calculate confidence interval for regression coefficients to assess their precision and reliability too. If we find that there is relationship between dependent and independent variables, we can check whether this relationship is significant or not using hypothesis testing. Here we use t-test to test whether the relationship is significant or not. We can use the following formula if we have to calculate manually. Otherwise we can use Excel or other software to calculate t-stat. Here we found t-stat 3.329, which is greater than critical value, so we're going to reject S0. It means there is sufficient evidence of a linear association at the 5% level of significance. Here we can see the graph for different predicted, estimated, and actual values. Here is the confidence interval for estimate for the mean value of y given a particular value of xi. And we can use our result and put these values in our equation, and we can find the estimated predicted value of yi. And for the confidence interval, we have already discussed that we can use many software, and confidence intervals provide a range of values within which we are confident that the true parameters lies with some certainty. There are some pitfalls of regression analysis too. Lacking an awareness of the assumptions underlying least square regression. What we do generally, we just perform regression analysis when we have value of x and y, but we forget to test whether the values of x and y satisfies the assumptions for linear regression or not. But actually we have to examine the assumptions, and we can only perform regression if the assumptions are satisfied. For that purpose, before running regression analysis, we can just use a scatter plot to see whether the relationship between x and y exists or not. And also we can perform residual analysis to check the assumptions. If there is any violation of any assumption, we can we can use alternative methods or models, or we can use some transformation on the data to remove the violation of the normality assumptions. I hope this will help you to understand the linear regression analysis, and specifically it is confined to one dependent and one independent variable. It is simple linear regression equation. Thank you for your time and patience. We'll see you again. Thank you.